What we're going to do is we're going to look at what's called qualitative analysis. Now, qualitative analysis is just occurs when we take a solution and we use its physical properties as well as the ability to form precipitate to identify the potential cations and anions that are in the solution. Traditionally, three factors are commonly used to determine what is in a solution. The first thing that we use is the solution color. Then we can use what's called a flame test. And finally, we use a double displacement reaction often as well. So many of our cations and some of our anions have caused the color of the solution to change. So for example, we can see here in this chart. So if I had a blue solution, that would suggest that my solution contains either copper-2 or chromium-2 ions. And then I could do further analysis to see which one it is. A flame test is a second way that we could qualitatively analyze a solution. And what it does is when the color, if we introduce a small amount of the solution into it, the cation or anion will change the color of the flame, and we can use the flame's new color to determine what's in the solution. So for example, if I had a blue solution that suggested that either copper or chromium was present, then what I could do is I could then take that solution and put it into the flame of a Bunsen burner. And depending on the color that it turns, that would allow me to then distinguish whether it was copper-2 or chromium-2. And so if I got a blue green flame, then what that would tell me is that my blue solution is most likely blue as a result of copper-2 ion and not chromium-2 ion. Now, the third and most powerful technique for determining what's in a solution is if we add a series of test solutions looking for the formation of a precipitate. And so what we do is we look for a cation or anion in our test solution that will cause the ions in our solution that we're analyzing to form insoluble compounds. And from the formation of those insoluble compounds, we then can deduce what's in solution. Okay. Now, if I'm testing for cations, I can use a flowchart to show my thought process. And the first thing I have to do is I have to find some anions that can be used to distinguish the cations present. Then I'll put them into the test solution, I'll add them, and I can do a flowchart. Likewise, if I want to look for anions, then I would have to look for cations that would cause any of the possible anions in solution precipitate out. So how does this work? So let's say I have a solution that potentially contains strontium ion and or iron 2 ion. What I would first need to do is determine any anions that would cause either of these two to precipitate. So I would get my solubility table, and with my solubility table I would look for anions that cause them both to precipitate. After I've identified anions that would cause them both to precipitate, then I would look for ones that are unique. And so in this case, I wouldn't use carbonate, phosphate, or sulfite because it causes both strontium-2 and iron-2 to form insoluble compounds. Rather, I would look for anions that are unique. So for my iron-2, I could use hydroxide ion because it would form iron-2 and hydroxide ion would result in the formation of an insoluble compound, whereas strontium ion and hydroxide ion would not form an insoluble compound. Therefore, if I added a testing solution that contained hydroxide ion and a precipitate formed, I could then suggest that it's due to the possible presence of iron. So, if I have my solution that potentially contains it, I need to add a testing solution. Now, I cannot add just the anion. It has to be part of an ionic compound. So therefore, I want to combine the anion that I need to use for my test with a cation that will not get in the way. So we usually use group 1 cations. This means that my testing solution is not hydroxide ion, but really is sodium hydroxide. Now when I add my sodium hydroxide to my sample, I have two possible outcomes. The first outcome is that a precipitate forms. And if a precipitate forms, then I can conclude that the solution contains iron 2 ion. Because I know that iron 2 ions with hydroxide ions will form an insoluble compound. So I can say that my precipitate is iron 2 hydroxide. My other possible outcome is no precipitate. And if no precipitate forms, the only conclusion I can make is that the solution does not contain iron 2 ions. I cannot say anything about whether or not strontium ion is present at this point, because the addition of hydroxide ion only allowed me to test for the iron 2 ion. Now, if a precipitate has formed, I need to remove it so that I can do further tests, because I don't want any solid that's present to interfere with further analysis. So as a result, what we do is we filter it. And so after I filter it, I take the solution that passes through my filter. The solid iron 2 hydroxide, if it was present, would be removed, and I'm left with a solution that may possibly contain my strontium ions. So now I can take my solution that possibly contains strontium ions and add to it a testing solution that would cause a precipitate with strontium. So therefore I'm going to use the sodium sulfate solution. Again, it's the sulfate ion that I'm interested in, but it has to be part of a compound. And so I'll add my sodium sulfate solution to my solution that possibly contains my strontium ion. And just like when I added the sodium hydroxide, I have two possible outcomes. A precipitate could form, or no precipitate could form. If a precipitate forms, then I can conclude that the solution contains strontium ions, and that my precipitate is strontium sulfate. If no precipitate forms, the only thing I can conclude is that the solution does not contain strontium ions.
Okay, so here we have a possible solution that contains both sulfate and or chloride. So what we're going to do is we're going to go through the steps to develop our flowchart. So just like before, the first thing that we need to do is we need to make a list of, in this case, not anions, but cations that would cause each of them to precipitate. And so what I would do is I would write my chloride, and I would make a list. Okay, and so now I have my list, and then what I would do is I would go through the list and I would remove anything that's found in both. Now sometimes we'll find that one of the ions doesn't have anything unique and the other one does, in which case the order in which we do them matters. So I'm actually going to do this in order, and so I'm going to pick this. And I'm going to say that I don't have any of these ions present. I only have that. And so I have this ion, a solution with this cation, and a good testing solution involving that cation would be a calcium nitrate solution. And we want to pick a calcium nitrate solution so that the nitrate doesn't get in the way. And then the only other testing solution I have present is a silver nitrate. Now, I know that silver ion would cause both of these to precipitate out. And so, therefore, what's important is the order in which I do them. And so, if I test for and remove any potential sulfate first, then any precipitate with the silver ion can be attributed to chloride. So the order matters. And so I want to test for sulfate first, and to do that I'm going to use a calcium ion, and my testing solution will be calcium nitrate. So therefore, I'll come over here and I'll add my testing solution. And it's going to be a calcium nitrate solution. And when we do this, we have our two possibilities. We have a precipitate, or we have no precipitate. Okay. And what we can say is, if a precipitate forms, my sulfide ion is present, and the precipitate is our calcium sulfate. If no precipitate is formed, then all we can say is no sulfate ion is present. We cannot say anything about whether or not the chloride ion is present, because neither one of them could be there. So we want to just remove any potential sulfate ion, sulfate precipitate that might be there. So we'll filter it. And because we make sure we add enough calcium to remove all of the sulfate, we'll filter out and remove all of the sulfate. So now I'm left only with a solution which may contain my chloride ion. So now, in this case, if I use my silver as my silver ion as my testing reagent, it won't get in the way. Remember, we can't add just straight silver ion. It has to be part of a solution. And so again, we'll use the silver nitrate. We'll combine the silver ion with a nitrate ion to get our solution, because the nitrate ion will not get in the way. And again, we have our no precipitate or precipitate options. Okay, and we can say if a precipitate forms, then chloride ion is present. And our precipitate is silver chloride. And if no precipitate is formed, all we can say is chloride ion is not present. Now, the order in which we did this test is extremely important, because if I had added my silver nitrate first and I got a precipitate, I would not have been able to say if it was due to the sulfate or the chloride ion. Only because I added my calcium nitrate and I showed that there was no sulfate, or I removed the sulfate, could then I attribute any precipitate due to the silver nitrate as being either as being due to chloride.